Okay, let's dive right into this. Welcome to today's Explainer, where we're going to untangle a pretty fascinating mathematical mystery. Now, if you've done any work in calculus or complex analysis, you already know power series are basically the Swiss Army knives of math. But sometimes they behave in ways that feel totally counterintuitive. So today, we're locking in on exactly how power series converge correctly.
To figure this out, we're going to use a perfectly simple, totally well-behaved rational function. Just f of x equals 1 over x plus 2. Now, our main goal here is to transform this straightforward algebraic fraction into a power series. But as you're going to see in a minute, the way we actually choose to do that, it changes absolutely everything. Which brings us to the central paradox of this whole explainer. How exactly can one single function give us completely different series representations? Like, how does the exact same mathematical curve manage to wear completely different disguises just based on where we're standing? Well, let's find out.
All right, case 1, center 0. Let's start by anchoring ourselves right at the origin. So we're going to build a power series firmly tethered to 0. To pull this off, we basically need to massage our function into that classic geometric series format. You know, the 1 over 1 minus r. First step, we factor out a 1/2 from the denominator, rewriting the whole thing as 1/2 times 1 over 1 plus x over 2. Then step 2, to get that crucial minus sign we need, we define our r as negative x over 2. Finally, step 3, we just drop that right into our geometric series sum formula. The result? We end up with 1/2 times the infinite sum of negative x over 2, all raised to the power of n.
Now, because the terms in this new expansion are just powers of x, which, let's be honest, is really just a fancy way of saying x minus 0, our series is centered exactly at 0. This is our anchor point for right now. But here's the thing. Power series are demanding. They don't just work everywhere magically. For a geometric series to actually converge, the absolute value of our ratio, r, has to be strictly less than 1. So we take the absolute value of negative x over 2 and we set in less than 1. Multiply both sides by 2, and the math clearly tells us that the absolute value of x must be less than 2. And boom, that is our safe zone.
So that brings our radius of convergence to exactly 2. I like to think of our center at 0 kind of like a campfire out in the dark. The radius is basically the reach of that firelight. For this specific setup, the light and warmth extend outward for exactly 2 mathematical units in either direction before the dark, or, well, divergence takes over. And what happens at the very edge of that firelight? Well, if we test the exact boundaries, plugging x equals 2 and x equals negative 2 back into our series, the resulting sums diverge. They just spiral totally out of control. That tells us the strict boundaries themselves are not safe. We literally can't include them in our zone. So, wrapping up case 1, we can establish our final interval of convergence, the open interval from negative 2 to positive 2. This right here is the exact, exclusive territory where our first series representation accurately mimics our original function. Okay, let's move on to case 2, shifting centers. Let's see how this builds. What happens if we decide, you know what, we don't want to camp at 0 anymore? We take the exact same function, 1 over x plus 2, but we take it down a totally different algebraic pathway. Step 1, we cleverly rewrite that denominator as 1 minus the quantity negative x minus 1. Step 2, this makes our new r value negative x minus 1. And for step 3, we expand it using our geometric formula, arriving at the sum of negative 1 to the n times x plus 1 to the n. Take a second to notice the structure of our new terms. They're all based on the quantity x plus 1. In math terms, that's just x minus negative 1, right? So our new anchor, our new center, is negative 1. We have officially moved the campfire. Now we've got to calculate the safe zone for this new campsite. The geometric rule? That stays exactly the same. The absolute value of r must be less than 1. So the absolute value of negative x minus 1 has to be less than 1. Which mathematically is exactly the same as saying the absolute value of x plus 1 is less than 1. Unpack that inequality, and we get our new bounds. X must be strictly between negative 2 and 0. And right away, we hit a massive realization. Look at our radius. For this second series, the light of our campfire only reaches out 1 unit. And just like before, if we check the literal endpoints of this interval at 0 and negative 2, we get divergent series. Our mathematical firelight strictly stops right before those exact points, firmly locking in our new open interval. Now, what's really interesting here is when you look at the direct visual comparison. On the left, our first attempt, centered at 0, gave us this massive, sprawling interval from -2 all the way to +2. But on the right, our second attempt, for the exact same function, is awkwardly cramped between -2 and 0. And this is the million-dollar question, right? Why? I mean, it's the exact same mathematical function, 1 over x plus 2. Why on earth does merely shifting the center of our expansion violently shrink our convergence zone? What invisible force is in the background crushing a radius?
Section 3. Spotting the singularity. Let's track down this hidden culprit.
To solve this mystery, we've got to go hunting. This mathematical culprit dictating the rules from the shadows is called a singularity. Basically, a singularity is the exact point where a function breaks down and just becomes completely undefined. Look back at our original function, 1 over x plus 2. What happens if you plug in -2? You get 1 divided by 0. The universe explodes. At x equals -2, our function hits a solid, impenetrable, undefined brick wall. And here is the golden rule of power series. The rule that explains literally everything we've seen today. The radius of convergence is always exactly equal to the distance from your chosen center to the nearest singularity. That singularity acts as a strict physical roadblock to our campfire's light. The light simply cannot pass. Let's connect this right back to our evidence. In case 1, we built our campfire at 0. The brick wall is at -2. The distance between 0 and -2 is exactly 2. Hence, our radius was 2. Makes perfect sense. But in case 2, we moved our campfire to -1. We essentially pitched our tent right next to the brick wall. The distance from -1 to -2 is just 1. The closer you start to the wall, the smaller your radius has to be before you crash right into it. Section 4. The final comparison. Let's bring all this evidence together. This brilliantly illustrates the entire story side by side. On the top row, anchoring at 0 gives us the breathing room of a radius of 2. But on the bottom row, shifting that center to -1 chokes our radius down to 1. The function is completely identical, but the center dictates the distance to the nearest singularity, and that distance ruthlessly dictates your interval of convergence. You can reshape the algebraic identity of the function all you want, but you can never, ever bypass that singularity. But wait, actually, scratch that. We only looked at a simple singularity right here on the real number line today. So the really crucial takeaway, and the question I want to leave you with, is this. What if a function has singularities hiding off the number line way out in the complex plane? If the roadblock is completely invisible to the real numbers, how does that shape your radius? Keep that in the back of your mind as you continue exploring mathematics. Thanks for watching this explainer, and definitely stay curious.